Do you want to just close the door? Okay, thanks. Thanks everyone for joining us for what I hope will be an informative 2 days of conversation and discussion. To introduce basically the 2-day event, I just want to kind of give a slight overview of the program as we have guests who are also visiting and a distinguished group of critics who are going to help us shape the conversation. For those who may not know, the Design Research Lab is a 16-month course. It's very much a studio-oriented, self-organized platform for research. We very much embrace a kind of open framework for looking at design and how it can sort of facilitate varied kind of approaches towards problems of materiality, of systems, of spatial kind of formations. And you will see as a product of all of that what we're doing now under an umbrella agenda that we have called behavioral complexity. The course basically runs on 3 or 4 years, large kind of speculative question research platforms. And in that, we have 4 studios that basically are responding to that theme. The agenda this year of behavioral complexity is something that we're trying to explore that is more looking at design and architecture through scenario, through behavior. If that manifests itself in material forms, life cycles, space-changing production, in terms of robotics, non-standard ways of thinking through space, or if that is something about social interactions and the forms of governance that are going to sort of deploy these systems within the world. We take a very proactive approach in exploring these kind of different kind of design platforms, exploring new tools, and in some sense trying to get an active dialogue within the studio in terms of where this work could go. What we've organized in terms of today and tomorrow, we will have a morning session and an afternoon session. We're going to see today 3 teams. We'll break for lunch and we'll kick off again for another 3 teams, followed by a keynote lecturer, which will be John Fraser tonight. We will continue this next day, so it's a pretty hardcore event, so everybody get comfortable. And in terms of the critics, we're quite pleased to say that we have a very distinguished group of people coming to visit, starting with Marta Malay Alamani, who's been a longtime friend of the course, teacher in the DRL, critic, provocateur. She's been teaching at many schools from EAC to SciArc and has always been very proactive in helping us explore some of the issues that, particularly within material agency within the studio. Ed Mosley is our technical consultant from AKT, but he's also very much a part of basically what we do within the course, bringing an engineering discipline in terms of how we develop kind of structuring systems and so forth. John Fraser, who's our keynote, as I mentioned, is a professor of evolutionary digital design. He's a longtime teacher at the AA, And today he'll be speaking particularly about the issues of computation relative to the history of that within the school. So we're looking forward to the talk tonight. We have Dave Pigram, who is joining us. He is on sabbatical from UTS in Sydney, currently a researcher at the moment at Block Research and also a professor from Michigan. We have Jason Kelly Johnson, who is joining us from the West Coast, a teacher at a college called CCA, and also a practitioner with his wife, Natalie, of a very interesting studio called Future Cities Lab. We have Philip Block of Block Research, also a very distinguished researcher developing strategies for shell designs and others. And we have Max Wittella, who is joining us from Germany, a very interesting young architect, the particular researcher within mobility, which is a component of a lot of the research that we're doing here today. We're going to be joined by other critics like Mark Cousins, who is head of our PhD, head of history and theories in the undergraduate at the moment, and Mario Carpo from the Bartlett and Yale. The four studios, just to give a really quick overview, that are going to be a product of what you're going to see today. Patrick Schumacher is running one of the studios with Pier Andrea, and they've been looking particularly at exploring kind of relationships between parametric principles of parametricism relative to the house and the vehicle, and trying to find a synergy between performance design and how that kind of correlates within systems. We have Sajay Bhushan, who is developing a studio that is rethinking and augmenting existing kind of robotic facilities, developing concepts of phase changing and end effector development so that we could consider a kind of different kind of deployment of some of these kind of production-oriented systems and how they can be deployed in a new and novel way. We have Rob Stewart-Smith, who's working with Tyson, who've been developing a strategy of looking at swarm printing and quad rotor design for an airborne kind of system in terms of creating a strategy of production that can be deployed real-time and responsive. And myself, Theo Sparopoulos, working with Mustafa, who've been looking at the issues of self-awareness and self-structuring, particularly in rethinking modular robotics for architecture. So with that, I'm not going to bore you with an introduction anymore. I'll let the students situate their work relative to the process and the path that they've all have gone through. Each of the teams will mention the studio that they're situated within, but the studio is very much a collective, team-oriented teaching. We meet every 2 weeks with all of the studios, and it's very much a place of conversation and discussion. So with that, I will give it over for the first team, and thank everybody for joining us today.
Good morning. My name is Nick with my colleague.
My name is Wins.
My name is Ewan.
My name is Meng Xian.
And we are from Team xstrata. So we are presenting our design research titled From Tectonics. So our main material, our main research driver is foam, which is expanded foam, and the possibilities for different geometrical configurations and its formative possibilities inspired us to pursue this research. In terms of the material being the design driver, we applied the material into methods for generating design through dynamic relaxation for form finding. Next, we populate the particles on the form to distribute the nodes and the positions for the connections point and to result in a network topology. As a thesis, how we position our research is to speculate, activate, and reinterface a prototypical urban site. The main components of the research is a rapidly deployed automated robotic production process and with the material having the properties of a performative, lightweight, and adaptable material system. So the design process, we are also challenging the notion of translation from the digital to fabrication, whereby the input for the geometries are implicit in the material formation. Therefore, the description of the geometries of the form is directly encoded into the material. So on the automated manufacturing process, we are employing industrial robots for the production of the material due to its high precision, its time-based formative process, and the on-site assembly process. We are making a statement of the design being on the domain of the designer and the production being in the domain of automated manufacturing. So to position our project in a prototypical condition, we propose a street market to highlight to demonstrate the possibilities of the project. So the three main components of the application parameters are time-based, event-based, and environmental and contextual. The contextual being the adaptive possibilities and strengths of the material itself, where it is very much adaptable and highly configurable due to its reassembly notions of manufacturing and deployment. In terms of time-based, the growth speculation of the system is integrated into the building lifespan, whereby the project is not considered a highly permanent structure, but it can be adapted to use and events. In terms of research, historically, industrial production is driven mainly for efficiency and cost. So the historical basis for industrial production results in a highly standardized components of production components, which results in highly standardized products. Foam in architecture is used mainly for cast formwork, whereby on the right you can see a Mandela vet build a bridge using foam, which is milled out in CNC and then cast concrete to build a bridge. On the left, huge EPS blocks are milled out to construct a bus shelter. Excuse me. Our research is based on Marian Coletti's research work on foam tectonics, which we project our material processes and speculation on his research. So the main differences between Marian Coletti's work and our work is we decided to pursue it further in terms of the nodal configurations in a tectonic network of structure. Space grids and nodes are mainly used to increase the performative aspects of the structure, whereby because of the complexity of the production of the nodes, the nodes are highly standardized in the production of the components. This is a comparison of a production process for a complex node, whereby on the left side you can see a 3D printed node, which takes 20 hours to produce one component, and comparing it to our material system would take 2 hours to produce.
This is the disadvantage. The advantage from our material is based on the phrase changing material, and it can be rapid construct with single elements, and it can be easily applied with the robot to produce the multi-direction node to work in a more efficient structure system, and it also reduces the time and the cost based on the robot production, and it works well for the compression and tensile structure and to creating a self-support structure network.
Based on some basic additives and process Marion Colantes research said before, we did some more material part research. This is additives investigation. So in order to make material behavior better, we did some different additives, and then we get our proportion and additives. This is like some experiments we did to reinforcement our material system. One is to pulling another kind of material on our foam thing, another is coating with others. Then we decided to coat with resin. It make it stronger. And this one shows how time influence our material behavior. So the most interesting thing we set for our material system is like time-based behavior. So like this is same amount of material pulling to the same height. The longer the rest time set, we need more strength to pulling it. And also we can get different curvature of the elements, which we can input to our system. And these are some force distribution analysis we set for our element. From this analysis, we can tell the more plates it pulling, it shows more evenly force distribute. Like from these are the node reconstructions which can help us to to calculate the material amount. Then we did some load tests for our material system. This is same amount of material, but different density. It shows the more dense it has, it can take more compression load. And also with same setting, but different coat of resin, with the height of the 14 centimeters and coated with resin of 33 grams, it can take almost 100 kilograms. These are the tensile tests we did. Then we found it can take more tensile load with material-to-material connection and a coat with resin connection.
This is why we're using the robot, because we just translate a very simple path, and from the simple to creating the complexity material behavior to create multi-direction nodes. This is the simulation with 2 robots pulling by 3 plates and 4 plates. And this is the standard production from the one-to-one model. This is the 4 plates pulling. And we found it in the one-to-one scale, the gravity in fact much with the material. So if it is earlier, so the material starts falling. So this is a failure test. And we assume that we can, if we have more robots, then we can do the multi-direction pulling in the meantime during the robot collaborations. And this is our first step to manually figure out the production process. After we're pulling each element, we cut the plates, and then we wait it dry and put the material on the cutting section and pulling the next multi-direction nodes. And this is following the material connect to material, we manually control the geometry curve. And this is the first time we figure out the scale of our elements with the space created by the models.
So for the connections of the material, there are 4 conditions of connections, whereby 2 are end effectors interfacing with the material plates, and 2 anchor conditions, 1 on the surface and 1 from plate to plate. The plate to plate allows us to segment the components into assembly parts. This is an iteration of the end effectors, which is the version 4. Various studies were made on the connectivity because of the goal of minimal actuation and simplified force distribution to carry out the process. This is the exploded view of the final end effector, which we use for the one-to-one prototype at RoboFold. The communication is handled by IR infrared remote control to actuate the gripping process of the material plate. So for the hot wire, this is needed to accurately control the cutting locations of the material to enable the material continuity and material fusion for the next element. This is at the one-to-one production of the prototype. The material, it burns, therefore a lot of smoke was produced. Therefore, we are arguing for a contained production cell for the robotics. Therefore, we are arguing for a lights-out manufacturing, whereby no humans are involved. These are iterations for the material to plate interface. The current design is to allow us to assemble different parts of the modules to connect with each other. The bottom plates are surface locking, where we are able to engage and disengage the components individually. These are details of the pin connections, whereby is self-locking based on spring-loaded actuation joints. This is a detail of the anchor condition at the surface. This can be applied on a vertical surface such as wall or a horizontal surface on the ground.
This is the production procedure for the one-to-one prototype. We are trying to add in the complexity of the path during the material distribution to try to make it as automated as it can. And then we do the cutting automated and collecting place automated and pulling automated. And this is the one-to-one final model. And we also show the place-to-place connection. We break down into 3 parts, and after finish, we assembling each part together. And this is the proposal for the resin coating. We're using the spray to finish this kind of work after the robot cell production. And this is the conclusion of the whole process of the robotic production. We design the geometry based on the system and translate the data to the robot's moving paths. And then we assume that the material preparation and hot wire cutting and pulling and bioresin can all be automated. And we focus on the robot cell production, and we will manually assembling on site.
This is four-man tasks of automated robotic production, one is material preparation and placing and pulling elements and hot wire cutting. This is like a robot cell doing the one-piece job in the container. They will pick up plates first and then place them in the position. The top robot will do the deposit of material job, and then the 5 robots will do the pulling element. And after that, they will deliver to be coated with resin and then deliver on site to be assembled. This is some robotic configuration we did to figure out the robot's reach map. And then we found to increase the efficiency of the robots, we can distribute different jobs on the same level because we have different number of plates pulling nodes. This is from a container to robot cell. One container can be separated in 3 parts. One is equipment storage, and then is the main part of the robotic production cell, and then is the bioresin coating room. Then it will deliver to be assembled.
From our material system, our elements give certain limitations, such as angles and size. The angle between 2 branches has a reasonable range, which is within 60 degrees to 150. If the angle is so small, the fibers between 2 plates cannot be stretched fully. So it cannot give us a very natural curve. Based on the angle limitations, we know when we use the maximal angle branches, we can get our maximal span geometrically. Without this curvature is the maximal curvature we can get. Based on the experiment of our material, we know that our material is both good at compression and tension. So we use dynamic relaxation as our general foam finding method. There are all catalogs about the different set conditions. Compared to the normal modular component system, our branches are, our components are fully differentiated. So they are based on a natural curve. They are very easily to close loops. So these are diagrams to show different loops comes from the different combination of components. On the diagrams show we introduce Vernari logic as our method to generate our branch system, because when we populate different points, it can give us different latticing network. This is our step of our general system. We set different anchor conditions and make the dynamic relaxation and break down our mesh into our assembled parts and populate points on it, and then make the shape. Because the Vernari can generate some very short edge, and then we set our rule to merge two short vertices. From our material system, we know that our branches, the maximal number of branches is 6. So this video show in the system, they will try to merge merge the node which the branches in is more than 6. Based on the natural curvature, we define 2 kinds of curvature, which is positive and negative. And for the positive curvature, we have some extra branches pops up, so we can suspend some extra external surface on membrane. They are all catalogs based on the dynamic relaxation. And they also show the component number and the production time the robot cell should make.
So we applied this system into various street conditions to highlight the adaptability to different contexts. This is the street conditions. This is a type of spaces, and we are based on symmetrical conditions. The material system is able to adapt itself to various conditions, and at the same time being able to be highly differentiated in terms of the element geometries. This is the scenario that we are applying our highlighting our design project on. The yellow is to avoid contextual elements such as trees, buildings, and circulation paths. Thank you.
Can I ask you a question? What has been clear to me, I mean, I love the project, all the research, and also the results seem very convincing. No, first of all, congratulations. I really love the research and its various steps and aspects leading to a convincing application suggestion. But my question is simply, what wasn't clear to me is you start with the pulling off the actuation plates, and they become part of the structure in the end, or the whole or part of it, I guess. And I think that needs to be clarified to some extent, that double functionality. But then you have 2 ways of connecting. You have the way of material to material connecting, and the way of leaving it with the actuation component. I would understand it in terms of permanent and temporary or construction, but it seems you're mixing that in the model. Is that just here in the model, or what would be that? What motivates that potential mixture of these types of connections?
Ideally, we would prefer a homogeneous connection so that to ensure material fusion throughout the system. But we discovered that to close the loop, it's not possible to continue cutting and pulling from the cut plates. We also considered the assembly aspects of the project. Therefore, to segment the different components for assembly and the production cell constraints as well.
Actually, so leads to a follow-up question, because I was also wondering in terms of the production scenario. One way one could think of it is just off-site generation of these nodes and then shipment and assembly. It seems you're talking about shipping a whole production unit with multiple robots. So you want the robots not only to produce the nodes but to assemble the nodes, and you want to pull nodes off existing structures. So is that the way you see the scenario, rather than a component assembly? Yeah. And why are you thinking about it this way?
The robotic production is contained in the container cell because of the various hazards of the material itself. Foam is quite toxic in terms of the fumes generated, and because of the cutting process as well. For the assembly part, because of the material system is lightweight and is able to be carried humanly. So we are making a statement of human assembly because it relates to the urban needs and use. For example, if a shop owner wants a structure to be discarded off-site, he can do it by himself. That's how we envision the system or the assembly process.
Well, it seemed to have been an image where you have a half-created structure and then the robot is pulling off, like as if the robot come now here to half finished and then pull another node while using that as an existing backplate. Is that the way that's not the primary scenario?
That was
okay.
The manual pulling. We were figuring it out.
No, but there was also in one of the animations was done like this. It seemed to be where a cluster of robot emerges around a multi-component structure, rather than having these shipped in the crane and assembly. Yeah, okay.
I'm going to follow up a little bit on Patrick's comment. I think for me the biggest confusion that I still have, I think that there is many interesting things that have happened in the projects, at least since I last saw it. But the confusion is this. On the one hand, you seem to suggest, and maybe I got it wrong, but you seem to suggest that the material is phase changing and that there would be a possibility to reuse this material. You seem to be suggesting at some points. Then when you go into, we will coat it with resin, then the question of reuse of material begins to be a little bit a question mark. And with the issue about leaving the end effectors in the material, of course the question about how would you ever separate the foam from the end effectors is still there, very present. So I think that with this, what Patrick was saying about a permanent construction versus a temporal construction, this is really where the project, to me, is more ambiguous. In the sense that you seem to be claiming for a very fast type of construction system, and that also has the potential to be reused, but then everything that you explain in many ways seems to be locking things in place. Well, when Patrick says, well, but what if we were talking about a permanent construction, that the robots could be there directly on site, pulling from the nodes that have already been built, and basically what you facilitate as opposed to a standardized kind of production is that you make it happen while it's being built. And then you say, no, that's not what we are doing here. So this is, I think, where the ambiguity comes in. And it would be interesting, I think, that you clarify these two projects because both have a lot of potential, but they cannot be mixed. So when you do material-to-material connection, that is with the intention of reusing the material. But when you leave the end effectors, maybe it's with is a more permanent kind of construction that then you pull directly on the building side. But I think that the two mixed is what creates a lot of ambiguity, at least from my perspective.
I agree with what's been said before. I think there are a lot of positives in this project, but there are holes in it as well. And some of those aspects, things like the application of a resin after the production, is not really in keeping with the general processes that you've got, and you should have looked more at the additive approach and what that did for you. But again, the influence of temporary construction and permanent construction is one thing, but also the construction process with these end connections, they don't look like connections that people can actually get in and fix. And the actual process of construction is missing a few bits, which potentially will actually push it away from it being something that anyone can buy and do. So if you are looking for something that anyone can buy and do, then you need to have a system that anyone can understand. If you are looking for something that can be installed by robots or by professionals, then you can have a system that's more appropriate to that. There are a few other little things here and there, and I think but I think the general message is positive. I think the materials research was very impressive. I think your testing approach was very good and very thorough, and you covered a lot of the aspects that we needed to see. But I think it just got let down a little bit in the final application of some of that research.
Yeah, I'd like to. Okay, cool. Yeah, no, I'd like to follow up on the congratulations. I think there's a fantastic amount of development going on here. I guess I'd switch a little bit the comments and also point out a kind of question about the spatial positioning of the project. So your starting point is really great, that the space frame has kind of died because of the problem of the node, and that this material system solves the problem of the node. But I'm disappointed that you then said, okay, awesome, so everything now is a space frame because it's re-liberated. Because I think the material system is every bit as capable of doing, instead of point or node-to-node elongation to create a line, you could also have line end effectors and create planes, and suddenly you would open up this, which is, I think, an extremely rich monomaterial project, to have more propositions. So you could build walls, more wall-like things and so forth, and it could do a lot of work for you. Of course, the original reason of PU, or the primary use in architecture, is for insulation. So if you start to make things that aren't just structural lattices, then you could also actually leverage that aspect of the project. Finally, just a couple of very small comments. I think this question of the node is quite fundamental, as Patrick's picked up and Marta has followed on. One quite simple technical solution would be to make the nodes out of PU in the first place, prefab PU, and then you still maintain your monomaterial. And then a second comment would be that one of the advantages of your topologically malleable material is that you could embed things. So while stretching, you could have electrical cables and other things within your material. I think it would make this refabrication harder, but would kind of make more potent your proposition to architecture. So I think, yes, you're right to start with the space frame, but push it harder. I think there's a lot more things that your process could open up for buildings, for architecture.
Can I just follow up on that node thing? Because this is very interesting that we've got a project here which is all nodes, it's all joints. Reminds me of Conrad Waxman's kind of obsessional book about joints and joints and joints. But it is fascinating because what bugged the early history of industrialization was that what they fabricated in the factories was the easy bit, slabs and things, and left the hard bit, that is the joints on site, which was then the weakness, eventually causing the collapse of Ronan Point and so on. So I think that those comments are absolutely apposite, that once you start to move beyond the joint into a complete family of structural elements, then you might actually have a real answer to the sort of fundamental nature of the failure of industrialization in the previous century. So I think that's a fascinating proposition, and I think the fact that it's springing that proposition from the obsession with the nodes is a healthy thing. So I see it partly obsessional, partly dangerous, but in the end, probably the kind of inspiration and drive you might need to take this further. So congratulations.
I think for me, the most fascinating part of the project is sort of back in here where you're really trying to invent this kind of robotic cell. You're looking at different manufacturing kind of organizations that would begin to kind of create these things. And for me, that was really fascinating. And it definitely led me to think that perhaps one of the disappointing parts of the project is that you somehow didn't fundamentally question the use of these very expensive, very heavy, very, you know, the very typical, say these days, industrial robots. I was actually really excited in the presentation. There was a moment, and I just noticed it sitting right here. You know, you manufactured this little tiny machine using hobby servo motors and a couple Arduino boards. And there's something very informal and I think very robust about that kind of strategy. And it definitely made me wonder whether you need all of this heavy stuff to do this project. Or is there in fact a much smaller set of components that might be deployed on a site that could allow you to build these structures in a more kind of in situ fashion. One opportunity would be to really kind of question the robot arm and really be inventive about the construction of a new kind of machine. And another avenue that I think you could look at is, could the actuation mechanism itself in fact be embedded inside the component itself? Your components are actually large enough, something like pneumatics as an example, sort of embedding air motors, muscles within the component. And so they're actually formed potentially from within. And I know this might sound a little far out, and I'm inventing something that I really don't know if it's possible. But when I look at these, you know, it definitely feels like it might be a potential, and then it starts to feel like it's less of a kind of top-down and perhaps something that's much more informal and begins to sort of construct itself from within. And so I know that, in fact, you know, it's very much a project about looking at industrial robotic kind of production. So I think if that was your thesis, then you've done a really, I think, great job at it. But I can't help but wonder what the next, you know, kind of project might be in this genre. Something that might be more flexible, might be more built from within. And certainly, I think the foam offers an opportunity, but you really, I think, I mean, we saw the fumes. You're doing this, you know, you're creating cyanide in situ, and you're breathing in these things. You guys are all probably, you destroyed some brain cells making this project, which I think is really cool, right? But I mean, we've all been there. But you're not actually, you don't seem too worried about that. You know, I mean, I know that you're like, okay, we'll just do a robotic cell, but I wonder a little bit about that. Why not kind of question that and be inventive in a way around that? And so. But you know, it's an impressive body of work. But I think you haven't, in a way, questioned fundamentally enough the tools, let's say, and been inventive in that capacity. And so there's a little bit of for me, a bit of a problem there.
Yeah, impressive amount of work. I don't know when you guys did all of this, but. I had a few questions about, you went to applications, and then specifically with the form finding, you used dynamic relaxation to go to predominantly compressive and tensile members. But what I'm surprised is that you stick to all the examples that you created, all have a surface topology, so they're all more shells and things like that. And so I want to ask two things in this direction. So one is that the way that you create your nodes, they naturally create nodes that also have some bending capacity. So they're not just coming together in one pin, in one joint. And so actually for the shell-like structures or the surface-based structures, you could just leave it to one layer. So you're basically making all these shell structures as a double layer, severely over-dimensioned sandwich. And so that is the first comment. If you want to go to surface, then that is not necessary because your system already inherently has that bending capacity that allows you to go just one layer, for example. But then I also was expecting, and you only did it in the smaller scale, is that looking at just the size also of your components, what can one really realize with these kind of cellular kind of aggregations and spatial frameworks? And there I am, and perhaps that's why you went to the surface topologies in your demonstration, because there, yes, you can cover a walkway and so on, but what can you really do, and how can you really integrate these fully spatial cellular kind of aggregations of nodes inside a building or inside of something that can be used beyond just the structural element, right? And so that is something that I think is you avoided at a certain point. But obviously you had a lot of work to do in the material testing and the fabrication. But anyway, that's a comment, and perhaps you have some thoughts on that, or you tried and you avoided to present it to us here today, or what happened there?
I think that was discussed. Obviously these are mobile connections, and that's why it's actually never a space frame for cells. I never tried to label. And but in fact, it's not a shells, it's single layer, the way I understand it. But then using 3 nodal points to launch subsystems like the skipping, for instance, the stretching of the. So these must be. They get into bending. They operate in bending, I suspect, at points. Particularly if you have dynamic loads on these, because they're not a complete surface. They're not never triangulated. So I think that moment strength or bending strength is activated in the system. But it doesn't need to be everywhere. I mean, I think this could have been further explored because plate-to-plate connection might still be a hinge point, a light, simple connection because each node is internally strong. One could look at various structural systems. I mean, that discourse is needs a bit further, as well as a scaling discourse with which I believe is viable because of composite inherently. It mimics a kind of composite shell construction in the node. But yeah, I think that whole structural discourse is vital, but was part of the debate as far as
I think Philip's point is an important one because I think what this potentially could be is deployed with different kind of plate conditions, develop different kinds of resolutions because the material itself is really given definition through these kind of continuous kind of almost delaminations. So I think it's important, to speculate in terms of how this can be really fully functioning and fledged out as a lattice strategy and really take on board, I think, a lot of the foam aspects of this thing because the instantaneous aspect of it allows it, I think, potentially to think, like Jason was mentioning in terms of the end effectors, where the project is less robot and more end effector kind of deployments. And the surface strategies, I think, just the same way on a micro scale, you can make a sandwich panel. You could develop, I think, different kind of categories of stiffness where pliancy is something of great value in some aspects, particularly with interiors and so forth. And then that one can actually start to think about this beyond the surface topology of a generic shell deployment, but something that is actually really speculating on how these processes could work with different scales of operation. I think they tried to deploy it in one scale, in one sense to be coherent, but at some level I think that open experimentation should start to come back because primarily all of these nodes, the most exciting aspect of it is the fact that directionality doesn't really have a bias in a traditional way as other materials. So giving legibility to that, I think, is a design driver. It's not coming from the material, it's just a speculation where the material could actually find its form beyond the kind of relaxation and the optimization strategies. There should be a second microphone.
Sorry, just maybe something that came up also is what perhaps hasn't been talked about is that I think it's also a great flexible system to deal with tolerances and to just accept. Probably that was discussed in previous reviews. But to add one more structural thing is just for you guys to trigger as an input, perhaps you continue with this. I know you're at the end of a long DRL intensive period, but still. What's also what one notices in the models is that they have some flexibility. So they are stiff, but they also have this kind of bounciness. And that might be a very exciting possibility to deal, for example, in earthquakes or in kind of, so not to work with stiffness and with kind of a rigid, like, I'll brace all the forces that come at me, but actually to play with it a bit more like in lightweight design where facades are done with flexible cable net systems and so on. One could start to perhaps even imagine that these kind of systems start to absorb effects of earthquakes, start to absorb the wind, and that we don't over-design for the heaviest load case, but that we allow the structure to kind of work with the loadings that it takes. So perhaps that might be a nice future direction also to look at.
Want to carry on a little bit from what David Pigram was saying before. I mean, this is a monomaterial project, and where I find it particularly interesting is in the sense that when you start thinking about mass customization and all the kind of technology that's available now, it's quite easy to imagine layering lots of materials together and doing all kinds of complicated embedded things. And when you start to approach a monomaterial, and in this particular project, what we have is a very simple setup where all the complexity is actually happening in the fiber arrangements that take place through the actuation of the robots. And the fact that they can be controlled in n dimensions, well, in this case 6-axis, each independently, starts to suggest that we could actually do some very specific and customized things. And if we start to go beyond just the node and start thinking of line, plane, surface, volume, this is starting to become quite an interesting strategy for very strategic, very articulated material deployment that has a wealth of potential complexity in a monomaterial. And I think that's something that contributes in a very interesting way to our discussions today and also to another way of thinking of mass customization.
I'm really glad that the project kind of raises various questions or has various layers, including industrial automation versus structural mechanics and also details of what or design tectonics, from walls to what else it can do. So in that sense, I think it's a very provocative enough kind of project for you guys to set up your book and your articulation of the book in that sense. But in picking up what Marta was saying about the ambiguity, to me that is somewhat interesting. The ambiguity itself is its perhaps most interesting urban application, that it can change from being temporal, as and when program ossifies, you begin to make parts of the structure more permanent. So it has that temporality to it, or temporariness for a while, and then you start coating it with resin, and you can then perhaps spray it with concrete or make it more permanent in that sense. So that to me is an interesting urban application that comes directly from the temporary nature of the material. And it is true that it is perhaps quite toxic as in this particular arrangement of foam, but it is quite feasible to think of foams which are not as toxic but still have this kind of behavior. So in general, I think I should congratulate you on a wide range of things that you've tried to handle, from robotic productions to material quality and things that you've been obsessing over. So congratulations on that.
Yeah. Okay, just one last. Also, you've been super brave. I mean, testing the structural with your own body and taking that at risk. I think I was really impressed by the amount of work. I would recommend you next time, don't ever remind other people how toxic the material actually is. I mean, I almost forgot about it, and then you reminded us again. That brought me to the question, what is the inherent function of the material actually? And of course, it's about insulation. It's not about structure. We all know that. But then I was thinking how the kind of how this plate is actually defining what the material, what kind of job it will do. And so I was wondering, how can that interface that sits around here, and I'm sitting in front of that kind of almost Greek column there. It's like if the plate, the kind of parameter of your system changes, how can then the result be a different one? And I'm thinking, if it's insulation, why don't we think of rectangular input parameters, these plates that turn this material into walls and doing the job the material actually does? Just as kind of ideas that popped up in my head.